thanks everyone for coming. And I'm Kitty. A little bit about myself. I work at Microsoft in the quantum systems team. So quantum education and producing materials and content to teach the public and our customers is part of my day job. But I also have a passion for art. So I'm kind of trying to learn to combine science and technology with art together. So I have a background in condensed matter physics. So I did my PhD in applied physics in Harvard, and before that I was in University of Cambridge. Started with low temperature experiments, trying to study the quantum phenomena of materials. And I moved more and more towards applications and worked at Intel and then Microsoft, a lot of entrepreneurship and silicon photonics. So now I'm back in quantum. That's kind of where I started. So it's very exciting that this industry is emerging, and there's a lot interesting information out there. And quantum computing is a subject that involves a lot of different areas. There's math and physics. There's also software and hardware. So I hope that this class will background and have some pointers to start digging deeper into the subject. So we're not gonna do it in a crammed way. We're gonna have a soft landing. So it will be pretty short every week. We're gonna have 30 minutes to discuss a concept. So that also can include theory. There's also hardware aspects I will show people. And there's also programming that I can lead people to the places they can learn how they can start coding and programming on a quantum computer. So I have a project on Hackaday, and thanks Hackaday for hosting this virtual class. It's called Introduction to Quantum Computing, and it has a summary of this project. I started using comics to explain the concepts. Every Wednesday and Sunday, I would post an update, and information about the class will also be posted there. So you can follow there to look at what topic will be discussed for the week. It will help if you have seen this before we start this 30-minute discussion. And throughout the week, feel free to post comments, post questions, and discuss with your peers on the Hackaday project. And I want to make this very interactive, so it's not just me teaching. I'm also learning, so I would love to discuss with you online or offline, and we can learn together. And I would highly recommend that you take notes for some of the materials that we show here. Even though this is recorded, I want to encourage this reinforcement learning for natural intelligence, which means there will be materials that you will recall constantly. We may have covered some content a few days before, and now we are looking at it again from a different angle, and that will also provide me feedback. So feel free to ask questions during this class, and if you like to type your questions in the chat, feel free to do that. Sophie is monitoring. And you can also unmute yourself to ask the questions as we discuss. And if there's anything that is confusing, in any way, just ask, just raise the question. I cannot see you right now that I'm sharing my screen, but Sophie is monitoring the chat, and she can let me know if you are asking questions there, and I can try to explain that in a different way. So let's just take a few steps back to look at how computing has been developed to where we are, and right now is a perfect timing to start learning about quantum computing. So we are all very familiar with the technologies that rely on computing is pretty much everywhere. So all of our world functions rely on connectivity and technologies, and all of our problems we represented on a computer, and we send it online through the data centers, and that could connect to some other part of the world. But there are still some problems that our most powerful computers still run into limitations. Even our supercomputers and high performance computing clusters are not capable of solving some of the most challenging problems. Those problems include a lot of things that relies on the fundamental behaviors of nature. Things like chemical simulations or discovery of new materials. Those fundamentally are quantum mechanical. That's the interactions between molecules and fundamental particles that are so small and they work in a quantum mechanical way. Our classical computers may run into limitations when we're trying to capture the behaviors of those systems. And there are also problems such as logistics or signal processing or security that fundamentally they're classical, but with our advancement in quantum algorithms, they can also help solve some problems in those areas, even though they may not be themselves quantum mechanical. So I would later on dive into more of the specific applications. And also we have at Microsoft developed a lot of libraries that that provide solutions to some of these industries. There are blogs you can read over there, and there are also code samples that you can download and try running those examples yourself on your own computer. So generally speaking, there are several application areas. So quantum simulation to me is the most interesting area because my background is in physics and our classical computers are not able to simulate all of the quantum systems. So if we can have a computer that is itself quantum mechanical, then they can be able to simulate the quantum systems. And then there are algorithms. There are quite a few algorithms that's developed since the 80s that can lead to very exciting applications. And there is also cryptography that quantum computer can bring solutions to. Most of the modern cryptography relies on RSA, which is factorization of huge numbers that could take unreasonably long time for a supercomputer to figure out. But then if quantum algorithm comes in, it can break the current RSA method, which is terrible. A lot of banks and governments are looking into that in order to prevent such criminal act. But at the same time, if we can have a quantum computer generating new types of cryptography methods, that's even better. I would say that quantum computer is like the other biomimicking tools. So obviously these pictures here I show are kind of easy to see that we were inspired by animals to build tools. But then we can also be inspired by nature, the most small building blocks of nature to build computers. So this course will start looking into the fundamental basics of how quantum computing works. And I would not overload you with information. So that's why we only have 30 minutes and would just talk about one topic per week. And throughout the week, you can let me know what you want me to draw, and you can look at the comics to see what's coming up next. So quantum computers could help us solve some of the problems that current computers cannot do efficiently. But what is it? On a high level, it is based on the laws of quantum mechanics. It's a computation based on that. It has a relatively pretty short history. It developed really, really fast. So here is what I wanted to show, that it has a history since the 80s, when it was first proposed by Mann and Feynman that we could create some machines that's based on the laws of quantum mechanics, and that could help us build simulation tools to mimic quantum mechanical systems. And then from there, we had quite a few algorithms developed, and they are all based on each other. So there were the first proposed quantum Turing machine by David Deutsch, and then Peter Shor came up with an algorithm for factoring. And Groover then produced an algorithm for quantum search. And there were more, and most of the later algorithms relate to some of these existing ones. And those algorithms could be limiting themselves, but then they show that they could solve certain problems that's more efficient than classical computers, classical algorithms. And then since then, we all know that in the past couple of years, all these big companies have jumped onto the subject. So Google, IBM, Microsoft, Intel are all working on, and a lot more big companies and startups working on both the hardware and software development of this. So we are in a very exciting time that this emerging technology is growing into an industry. So, and it's also a perfect time for us to get into it before it's too late, to really try to demystify a lot of the things that we hear all the time from media. So we know that our classical computing is based on the binary systems, and the modern computers are made of transistors to represent zeros and ones. Quantum computers are fundamentally different. So classically, we can describe a system using bits, and note this definition of states is you can imagine it as a status or condition of your system. So say if your light is on or off, then you can represent it as 0 or 1, or 1 or 0. Say your temperature is too high or too low, that could also be represented as 1 or 0. Or if you flip a coin, the head and the tail could be 1 or 0. So all these metaphors that I chose are like conveniently binary. And mathematically, we can also just write it out as vectors. So 0 is in the two-dimensional space, and there are only two possible ways to represent the classical bits 0 and 1. So 0 we can just write 1, 0, and 1 as 0, 1. There are only these two possibilities for a basis of 2. And if you have more classical bits, you can just write it out as a combination of 2 bits. And the mathematics that's used here is called a tensor product. I've written out here how tensor product works. This is basically how you put two vectors together and then try to calculate the result of their tensor product. So the first one times these two, the second one times these two. So you can walk through the maths later. That's not critical right now. But using vector would make the representation very easy later on as we get more into it. But simply looking at this, you can also see that if we have two qubits, then that's 4 possible configurations, 4 possible ways to represent the two bits. 0, 0, 0, 1, 1, 0, 1, 1. There's no other possibilities. It turns out you can write it out. If you do the maths, you get this 1/4 vector. But even without doing this tensor product, you can see these are the 4 possible ways to arrange the numbers. 0, 0, you will have the 1 starting at the first element. And the second one will have the 1 here. The third one will have the 1 third. Fourth one will have 1 at the bottom. So that's a 4-dimensional, it's called Hilbert space. But don't worry about these terms. We'll just get more intuition. And we know that classical computers are built on transistors that would represent 0 and 1. And how transistors work, I won't go into details, but it's basically a semiconductor sandwich. You can have the electrons to go through your material or not based on the voltage you apply to the material. If you let, say, let the voltage or electricity go through, you can say that is 1. If you don't let it go through, you label it as 0. So that's how bits, classical bits, are physically made in computers. So I'm using quite a lot of analogies here, and quantum computing is a more correct way to describe nature, I would say. So it functions completely differently from this binary way of representing information. So a switch-like binary building block is 0 and 1 is a much more simplified version of how nature behaves. Nature, which is made of the fundamental particles and the quantum mechanical particles like electrons, photons, atoms, etc. They have energy states. So everything is built on top of these things. So at the very low level, they have the energy states that are in superposition. So it's not 0 or 1, but different states in a coexisting manner. So I'm gonna explain a bit about what superposition is, and that is the fundamental behavior for a quantum computer. So classical bits, again, you have 0 and 1 that you can make all kinds of metaphors to say that. So if I have a circle, if it's empty, we can label it as 0. If it's filled, it is a 1. For a quantum bit, shorthand qubit, it can represent 0 and 1 in a single qubit. So here you can say we have 1/3 of the state 0 and 2/3 of 1 in it. Another metaphor you can say, we have some lottery thing, and if we have 20 balls, if they're all red, they're 0, or blue, they're 1. But then if you mix it up, we can have arbitrary numbers here. So say 8/20 is 0 and 12/20 is 1. You can change any number here. And then a coin, you can also say a head is 0, a tail is 1. If it's an even coin, if you rotate it, you know that there's 50% chance of landing on 0 and 50% of landing on 1. So you see that here, the quantum bits, qubits, is related to the probabilities of the amount of information in there. So a spinning coin is a metaphor for head and tail in superposition. Again, representing it mathematically, I hope you made notes earlier to write down what 0 and 1s are. So a state for a qubit, we can again represent with a vector. But now, instead of just 0s and 1s in the vector, we can have amplitudes. We can have any number A or B. If you split it up, you will see that is A amount of 0 plus B amount of 1. So that is to say that a quantum qubit is a state that is a superposition between 0 and 1. And or another term is linear combination of these two possible states, and they each has a weight in front of them. So A and B tells you how much of 0 and 1 is in your whole system. The only requirement for them is that their amplitudes squared sum to 1. What does that mean? So in our earlier example, a circle with 1/3 of 0 and 2/3 of 3 is basically saying that the probability of finding the circle in 0 is 1/3. The probability of finding the circle in the black 1 is 2/3. So A squared and B squared are probabilities of how much of those possible outcomes you can get. So similarly with the other two metaphors, you can write it out. So common sense, when we have a complete system, all of the possible probabilities will add up to 1. So there's nothing more to that. This is called a normalization condition. So this is a simple way to represent a qubit. It is a linear combination of two possible states. If you have multiple qubits, you can do the same thing like before to have a tensor product between different qubits. So if you have 2 qubits, you do this tensor product again, you get 4 different amplitudes. And again, the amplitudes are the coefficients to tell you how much of these 4 possible states, 4 possible configurations that's in your system. And you get the probabilities of each, add them up, they should be 1. That's the only requirement for this to work. So that is a qubit. That is different from a classical bit that is just 0 and 1. A qubit is a state with superposition of all the possibilities. And I think I will stop here for today. We'll talk a bit more of the significance of this, why we use superposition, and what does this lead to, and give you a bit more intuition of the concepts later on. Hope this helps. Let's see, if anyone has questions, feel free to ask.